I finally did it! I got rid of the complexity!
Oh yeah?
Completely refactored. Every component is independent, fully configurable, clean separation of concerns. Honestly, the most elegant code I've ever written.
Nice. How do I render a button?
So you instantiate the button factory, pass it a config object and a theme object. It's completely decoupled now, beautifully simple. Then choose whether to extend the form element or the UI element, pass in your event handlers, register it with the component registry, add the event token, and then...
I need all of that to get a button?
Yes! The complexity is gone! I have a physics degree, and I've spent 20 years in software. And I keep finding that the laws that describe the physical world, they show up here too. This series is about naming those patterns so we can use them to make better decisions, recognize pitfalls before they happen, and build better software. You don't need to know any physics. I'll bring the physics, and we can nerd out together. And today, we're going to describe what I call the law of conservation of complexity. And it's not as complex as you think. In physics, energy is conserved. It doesn't vanish, it transforms. This is one of the fundamental laws of physics. It holds everywhere, always, without exception. No experiment has ever violated it. Take a ball dropped from height. At the top, it has potential energy, stored energy from its position. As it falls, that converts to kinetic energy, speed. And when it hits the ground, it splits. Some becomes heat, some becomes sound, some goes into deforming whatever it hit. If you know the height, you can calculate how fast it's moving just before impact. You can calculate how much heat is produced. You can account for all of it because the total is conserved. We use this law every day, often without even realizing it. Roller coasters are designed entirely around it. Engineers calculate exactly how tall the first drop needs to be to carry the car through every loop and turn after. No engine, just conservation of energy doing the math. But there's a more interesting example. Hybrid and electric cars. When you brake, a normal car converts kinetic energy into heat through friction. And that energy is gone, wasted. A hybrid doesn't throw it away. It converts that kinetic energy back into electricity and stores it in the battery for later. That's regenerative braking, and it works because energy is conserved. It just needed somewhere useful to go. And here's what makes it fascinating as an engineering problem. Some energy will always be lost to heat from friction. You can't fully escape it. The environment always takes its cut. So the engineering work, what makes these cars better and better every generation, is in minimizing that waste, converting as much as possible into something useful and losing as little as possible to heat. And that's the point. When you understand that energy is conserved, you can understand the system deeper, trace what's happening, predict behavior, design machines, build things that work the way you intend. The concept gives you leverage over the physical world. In software, we see something similar, and that idea has a name: conservation of complexity. Complexity is never destroyed. It moves around or gets converted from one form to another. Let's take a library. Say you're building a date formatting library. At its core, date formatting is wildly complex. Time zones, locale differences, daylight savings, edge cases, calendar systems, right-to-left date formats. The complexity is real and it's not going anywhere. So where does it live? If you expose all of that complexity to the consumer, every parameter, every flag, every edge case configuration, your API is powerful but brutal to use. Every developer who touches it has to understand the full problem space. The complexity lives up top with the consumer. But if you make a deliberate decision to absorb that into the library, sensible defaults, automatic locale detection, handling edge cases internally, your API becomes simple. One function called reasonable output. But there are trade-offs. The simple API is now more limited, less configurable. The underlying implementation has to make assumptions on behalf of the consumer. What time zone to default to, what locale to use by default, how to handle ambiguous input, what limited options to let the user provide, and what to assume so it doesn't get overly complicated again. The consumer gets a much faster, easier experience. But the underlying layers are now responsible for resolving complexities the consumer doesn't even need to know about. which is often exactly the right trade, but it's always a trade. And that's the real cost. The library author now owns those edge cases. Every weird time zone bug, every calendar exception, every locale quirk, that's yours now. You traded consumer complexity for maintainer complexity. The most beloved libraries in software are the ones where someone made that trade on purpose and saw it through completely. They said the person calling this function should not have to think about any of this. And then they went and thought about all of it, so you don't have to. But sometimes the trade goes the other way, not by design, but by accident. Someone simplifies an API without absorbing the complexity properly. And suddenly the consumer has to work around undocumented behavior, handle errors that should never have escaped, or read the source code just to understand what a function actually does. The complexity didn't go away. It just became invisible and harder to deal with. So the question is never, did we reduce complexity? The question is, who is holding it? And did we make that choice on purpose? And just like in the electric car scenario, some complexity will always be lost to friction. Undocumented assumptions, imperfect abstractions, edge cases nobody thought of. You can't eliminate that entirely. The environment always takes its cut. Team dynamics, legacy constraints, deadlines, things outside your control. The craft is in minimizing the waste, converting as much as possible into something useful and intentional, and losing as little as possible to the places nobody thought to look. That same decision plays out at a much larger scale. Think about Android versus Apple. Android gives you configurability. You can change launchers, sideload apps, tweak settings buried 6 menus deep. The complexity is up, visible to the user. Power users love it. But the user is holding a lot. Apple does more work underneath, so you do less work on top. The complexity moved down into the platform. The experience feels effortless because Apple absorbed the trade-off, made the assumptions, and decided what limited options to surface so it doesn't get overwhelming. Just like the library. Neither is wrong. They just made opposite bets about who should hold the complexity, and both of them made that bet deliberately. If complexity is conserved, if it never disappears, it only moves, then the worst thing you can do is make decisions about it accidentally. Refactor without asking where the complexity went. Add an abstraction layer without deciding who's absorbing what. Simplify an API without owning the assumptions you're now making on behalf of your consumer. Because that complexity will surface. Maybe not today, maybe not in your code, but somewhere downstream in a confused consumer, a brittle integration, a 2 a.m. production incident. It shows up. It always shows up. The skill isn't eliminating complexity. The skill is placing it deliberately. When you're designing a system, a library, a product, ask, who is the person holding this? Are they equipped to handle it? Is this the right layer for this decision to live? And are we being consistent so that 6 months from now, when someone new comes in or we come back to extend it, we know where the complexity is supposed to live and why? That consistency is what separates a system that ages well from one that becomes a maze nobody wants to touch. Complexity is conserved. You can't get rid of it, but you can be intentional about where it lives, who holds it, and whether that's the right call for your system and your users. That's the physics of software. If this resonated, or if you've seen complexity disappear in a refactor and then show up somewhere much worse, I'd love to hear about it in the comments. And if you're into this kind of thing, please subscribe. There's more physics where that came from. And remember, physics is awesome, software is human. See you next time.